Hello everyone, welcome to my virtual presentation for VTC 2024 Spring. My name is Yu Zhiheng, and today I'm excited to share with you our latest research work titled Environment Aware Codebook for RIS-Assisted MU-MISO Communications, Implementation and Performance Analysis. This paper is co-authored by An Jiancheng, Gan Lu, and Yan Chao, and we are thrilled to have it accepted at this prestigious conference. I will divide the presentation into 6 parts: background, system model, channel chaining-based protocol, theoretical performance analysis, simulation result, and conclusions. Firstly, we know that obtaining the accurate channel state information and optimizing the reflecting coefficients at the RIS constitute 2 major challenges in RIS-assisted wireless communication systems. Specifically, the optimization of RIS-RCS critically relying on the accurate channel state information. We know that the instantaneous CSI is challenging to obtain, while statistical CSI is easier to obtain and possesses a longer channel coherence time. The existing statistical CSI-based scheme performs a good adaptability to channel environments. However, it suffers from performance penalty for the scenery with rich scatterers compared to the optimum RIS configuration performance. Moreover, it exhibits poor scalability. Furthermore, we can enhance the performance of the RIS-assisted communication systems through the utilization of codebooks, which can strike a flexible trade-off between system performance and chaining overhead, and has a low complexity in passive beamforming. However, existing codebook schemes such as random codebooks and uniform codebooks usually entail significant chaining overhead and lack adaptability to channel environments. Moreover, it is important to note that the effect of channel estimation errors in channel chaining-based protocol has not been evaluated in previous research. Therefore, designing an environment-aware codebook scheme based on statistical CSI may enhance the adaptability to channel environments and strike a flexible trade-off between system performance and pilot overheads. Against this background, in this paper, we investigate the environment-aware codebook design in RIS-assisted multi-user MISO communication systems. As shown in Figure 1, we have a RIS-assisted multi-user communication systems. The number of the BS antennas is set to M. The number of the reflecting elements at the RIS is set to N. The number of the single antenna users is K. Then, the composite end-to-end channel from the BS to user K is given by the sum of cascaded channels and the direct channel, where the 3 channels represent the baseband equivalent channel from RIS to user K, from BS to RIS, and from BS to user K respectively. Phi denotes the reflection coefficients matrix of the RIS. Therefore, during the uplink channel estimation stage, we can obtain the pilot signal received at the BS, where PUL is the average power of the pilot samples, XK is the pilot sample transmitted from user K to BS, and Z is the additive white Gaussian noise at the BS. During the downlink stage, we have the downlink complex baseband signal received at user K, where omega I is the transmit beamforming vector of user I SI is the transmitted information sample of user I, and NK is the noise at the case user receiver. Besides, we adopt a quasi-static flat-fading channel model for all links, i.e., the channel parameters within a coherent block are time invariant. We introduce the baseband equivalent channel and take the channel from the RIS to the user K as an example, where beta R is the path loss of the channel, FR is the duration factor of the channel, HRK loss and HRK unloss represent the loss and unloss component of the channel. To design the environment-aware codebook and decide the optimum codeword used for assisting in downlink data transmission, in this paper, we propose a channel training-based protocol by dividing the codebook generation and the codeword configuration into two stages. As shown in Figure 2, it is the frame structure of the proposed protocol. Specifically, during the offline environment-aware codebook design stage, we first generate virtual channels based on statistical CSI, which includes the path loss, the loss component, and the distribution of the unloss component of the practical channels. Therefore, we can obtain the virtual RIS user K channel as the Q's training block, where HRK loss is the loss component of the virtual channel and it remains unchanged within each channel coherence block. HRKQ unloss is the unloss component of the Q's virtual channel and it is randomly generated following the same distribution with the practical channel. Furthermore, the virtual BS RIS and the BS user K channel are generated in the same way. After generating these virtual channels, we perform alternating optimization to obtain the environment-aware codebook. Specifically, the sum rate optimization problem of the MU-MISO communication system is shown like this. Here is the sum rate of the multiple users, and we notice that the constraint includes the RIS RCS and the total transmit power. We adopted the zero forcing beamforming to achieve inter-user interference elimination, and PQ donates the received power matrix in the alternating optimization algorithm. We adopted the successive refinement methods to optimize RCS as a RIS, and the classical water filling power allocation algorithm to perform transmit power allocation. Repeat for Q training blocks. We obtain the environment-aware codebook. It is important to know that all the aforementioned operations are conducted offline. Next, during the online RIS configuration stage, we perform composite channel estimation where we adopt the mutual orthogonal pilot design and consider the minimum pilot overhead T equal to K, and thus the least square estimate of the composite channel of the Q's training block can be obtained. Then we adopt the ZF precoder, and thus we can obtain Q sum rates corresponding to Q codewords generated offline. We select the optimum codeword corresponding to the maximum sum rate and adopt it into downlink data transmission. Then, we theoretically analyze the performance of the proposed environment-aware codebook in perfect and imperfect CSI scenarios. First, we introduce the influence of the channel estimation errors in proposed channel environment-aware codebook scheme in Figure 5. It can be seen that the channel estimation errors distort the composite end-to-end channels, which is shown by the green arrow. This results in that the optimum index with the channel estimation errors may not be correctly selected. Then, consider the errors in conventional channel estimation and passive beamforming schemes as shown in Figure 6, we can see that the effect of channel estimation arrows is reflected separately at each phase shift. Note that the influence of the channel estimation arrows is implicitly reflected in the selection of the index, whose effects are difficult to accurately characterize. We derived a tight upper bound of the received power. Specifically, for n much greater than 1, the average signal power received at the user in imperfect CSI, where f1, f2 are related to ratio factor and c is a constant. When the channel estimation errors are adequately small, the theoretical received power in the perfect CSI scenery can be obtained. And here are 4 special cases corresponding to different sceneries. Specifically, if FR approaches 0, it degenerates to random codebook schemes. If it approaches positive infinity, proposed scheme can achieve the optimum system performance. If the chaining overhand is set to 1, proposed scheme reduced to statistical CSI-based scheme, and if it is set to the maximum value, we arrive at the quadratic scaling law of the average received power with respect to n. To validate our hypothesis, we conducted corresponding simulations. Here are some settings of our simulation parameters. As shown in Figure 3a, we compare the achievable rate with the training overhand in perfect CSI scenery, and the result of the imperfect CSI scenery is shown in Figure 3b. It can be seen that the proposed scheme can gradually improve the achievable rate with the increase of the training overhand. Moreover, in both the scenery of perfect CSI and imperfect CSI, the derived theoretical performance bound serves a tight upper bound of the simulation results. Figure 4a evaluates the sum rate versus the total transmit power. We can observe a logarithmic increase relationship between the sum rate and the transmit power as Bs, which corresponds to our theoretical formula. Then, as shown in Figure 4b, we compare the sum rate with the number of RIS elements. It can be seen that with the increase of the RIS element n, the sum rate of the proposed scheme with diminishing return, which is due to the fact that a larger number of reflecting elements could reap more radiating energy by coherently superimposing or cascaded links. Next, Figure 4c examines the effect of the overhand on the performance of the proposed scheme. It is noted that as the training overhand Q increases, the proposed scheme gets a certain promotion in terms of the sum rate and always outperforms the random codebook scheme as it utilizes statistical CSI to design the RC. Finally, Figure 4d examines the effective sum rate versus the channel coherence time. We can observe in Figure 4d that the proposed scheme can flexibly adjust the training overhand according to the specific channel coherence time to achieve the highest effective sum rates. To sum up, in this paper, we proposed an environment-aware codebook design based on statistical CSI for RIS-assisted multi-user MISO communication systems. We consider the influence of the channel estimation errors on proposed codebook-based scheme. We derived the theoretical received power scaling law of the proposed scheme both in perfect and imperfect CSI scenarios, and it is shown that the proposed scheme can strike a flexible trade-off between performance and training overhand according to the specific channel coherence time. The following are some references of this paper. We hope that our work will be beneficial for future research and practical applications. Once again, I appreciate the opportunity given by VTC 2024 Spring to showcase our work. Thank you, everyone.